In this episode, we focus on a security promise that sounds simple but gets complicated fast when you look at how systems really work, which is the promise that stored data should stay private even if someone gets their hands on the storage. Data at rest is the phrase we use for information that is sitting on disk, in a database file, in a backup, or on removable media, and the question is what prevents that information from being read if the device is stolen, a disk is copied, or an attacker gains access to raw storage. Beginners sometimes think encryption is a single switch you turn on, but the real decisions involve scope, key handling, and understanding what threat you are actually trying to reduce. This is where the comparison between GNU Privacy Guard, GPG, and Linux Unified Key Setup 2, LUKS2, becomes useful because they represent two different approaches to encryption at rest, one focused on encrypting specific content and one focused on encrypting entire storage areas. We will also talk about keys, because encryption without key management is just a false sense of safety, and we will talk about what good enough means, because security is not absolute perfection. It is a set of choices that are appropriate for the risk and the environment. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. To start, define what encryption at rest is trying to protect against, because that tells you whether you want file level, object level, or full disk style protection. If your main concern is that a laptop could be lost or stolen, full disk encryption can be very effective because it protects most content automatically when the machine is powered off. If your main concern is that a specific document must be protected as it moves between people or is stored in backups, file-level encryption can be more appropriate because it travels with the file. If your main concern is that an attacker might gain access to the running system, encryption at rest is less helpful by itself because the system often needs access to the decrypted data to function, and the keys are likely available while the system is running. That does not mean encryption is useless. It means you must be honest about the threat boundary it addresses. Encryption at rest is strongest against offline access, such as someone reading a disk without going through your operating system controls. Once you frame the problem that way, the choice between GPG and LUKS2 becomes a choice about what you want to encrypt and when you need it decrypted. GPG is best understood as a tool for encrypting specific data objects, such as files, messages, or archives, where the encrypted result can be stored or shared independently of the system it came from. It is often used for protecting documents, for signing data to prove integrity, and for exchanging encrypted information between people. The key idea is that the encryption is tied to the object, not to the disk that happens to store it. That means you can encrypt a single file and send it somewhere, and it remains protected even if it is copied many times. GPG can use symmetric encryption, where the same secret encrypts and decrypts, or asymmetric encryption, where a public key encrypts and a private key decrypts. For beginners, the important takeaway is that GPG is flexible and portable, but it also requires you to choose what to encrypt and to manage keys for the people or systems that need access. If you forget to encrypt a file, it is not protected, so the protection depends on disciplined use and good workflow. LUKS2, by contrast, is designed for block device encryption, which means it protects storage at a lower level, such as a partition, a volume, or a whole disk. Instead of encrypting one file at a time, it encrypts the storage container that holds many files, and the file system sits on top of that encrypted container. This changes the user experience dramatically because once the device is unlocked, the system and applications can read and write files normally without needing to encrypt each file manually. For a laptop or a server with sensitive data, that convenience is a major advantage because it reduces human error and ensures that most data ends up protected by default when the device is at rest. LUKS2 also supports multiple key slots, which means you can have more than one way to unlock the same encrypted volume, such as different passphrase or integration with other key sources. The conceptual lesson is that LUKS2 is about protecting whole storage areas automatically, while GPG is about protecting specific content deliberately. Both are encryption, but the scope and workflow are very different. The key handling story is where many real-world failures happen, because encryption is only as strong as the secrecy and availability of the keys. With GPG, keys can be associated with people or systems, and you must protect private keys from theft while also ensuring legitimate users can access them when needed. If a private key is stolen, an attacker may decrypt data intended for that key, and if a private key is lost, the data may become permanently inaccessible. With LUKS2, the key is used to unlock the encrypted volume, and the system often relies on a passphrase, a key file, or a combination. The risk here is not only theft of the unlocked secret, but also availability, because losing the unlocked secret can mean losing the entire volume. This is why key backups, recovery plans, and careful handling of unlocked materials matter as much as the encryption algorithm itself. For a beginner, the central idea is that encryption is a promise you make to yourself about who can access data later, so you must plan for both security and recovery at the same time. A useful concept for understanding how LUKS2 works at a high level is that it separates the user-facing unlocked secrets from the actual data encryption keys. Instead of encrypting the whole disk directly with a passphrase, LUKS2 uses a master key for the volume and then protects that master key using one or more unlock mechanisms stored in its header area. That design is what allows multiple key slots, passphrase changes, and other management features without re-encrypting all data each time. Conceptually, you can think of the passphrase as a key that opens a safe that contains the real encryption key, not the key that encrypts every block directly. This also means the header area is important because it contains the metadata needed to unlock, and damage to that metadata can create recovery problems. Beginners do not need to memorize internal structures, but they should understand the difference between the thing you type and the thing that actually encrypts the data. That understanding makes it easier to reason about why you can add an additional unlock method or change a passphrase without rewriting the entire disk. With GPG, the equivalent high-level concept is that encryption can be done in a hybrid way, where asymmetric keys are used to protect a symmetric session key that encrypts the actual file content. This matters because asymmetric encryption alone is not efficient for large data, but it is useful for exchanging secrets securely. The hybrid approach lets you encrypt large files efficiently while still using public key cryptography for key distribution and access control. For beginners, the practical implication is that you can encrypt a file for one or more recipients by encrypting the session key for each recipient's public key. That supports sharing while keeping the file protected against anyone who does not have the matching private keys. It also means that protecting private keys is critical because the whole access model depends on private keys staying private. This is why key storage, passphrase protection on key material, and careful handling of key exports matter so much. Now we can address what good enough means, because in the real world, you rarely have unlimited time, unlimited budget, or perfect user behavior. Good enough begins with picking the right scope of encryption for the threat, and that often means choosing full disk or full volume encryption for devices that can be lost, while using file-level encryption for particularly sensitive documents that might move across systems. Good enough also means choosing strong, modern algorithms and avoiding weak or deprecated options. But at the Linux Plus level, you do not need to recite specific cipher names as long as you understand the principle of using current, widely trusted cryptography. Another part of good enough is having a recovery plan, because an encryption strategy that causes frequent lockouts or data loss events will be bypassed by users or will fail operationally. If users are constantly locked out, they will create insecure workarounds, like storing keys in unprotected places, which defeats the purpose. So good enough is the balance where the protection is strong enough for the risk, and the operational friction is low enough that people will actually follow it. It is also important to understand the limits of encryption at rest so you do not mistakenly believe it solves problems it cannot solve. If a system is running and unlocked, data is accessible to processes that have the right permissions, and an attacker who has gained control of the running system may be able to access decrypted data. That is not a failure of encryption, it is a boundary definition, because encryption at rest is primarily about protecting data when the storage is offline or when the system is not unlocked. This is why access controls, account safety, and service hardening remain crucial even when you encrypt everything on disk. Another limit is that encryption does not automatically manage data exposure through logs, temporary files, or backups unless those are also included in the encrypted scope. Full volume encryption helps with many of those, but there are still cases like network backups or exported data where the encrypted at-rest promise might not carry forward. A mature security mindset is to use encryption as one layer and to understand where it begins and ends. A common beginner mistake is to treat GPG and LUKS2 as competitors where one is always better, but in practice they solve different problems and often complement each other. LUKS2 can protect the entire disk so that if the hardware is stolen, the data is not easily readable. GPG can protect specific files so that if they are copied to an untrusted location, emailed, or stored in a cloud bucket, they remain protected. In other words, LUKS2 is very strong for device-level loss scenarios, and GPG is strong for data sharing and portability scenarios. Another mistake is to focus on encryption but ignore key lifecycle, such as how keys are generated, where they are stored, how they are rotated, and how recovery is handled. A perfect algorithm does not help if the key is stored in an obvious place or shared widely. These mistakes are important because they show up in exam questions as reasoning traps, where the correct answer is the one that aligns the control with the scenario rather than the one that sounds most technical. When thinking about keys in a practical way, it helps to separate the ideas of confidentiality and availability. Confidentiality is about preventing unauthorized access, while availability is about ensuring authorized access is possible when needed. With encryption at rest, you often increase confidentiality but can accidentally decrease availability if recovery is not planned. Good enough key handling usually includes protecting keys with strong secrets, limiting who can access them, and ensuring there is a secure backup or recovery mechanism that does not create a bigger vulnerability. For example, a recovery key stored in plain text on the same device is convenient but undermines confidentiality, while a recovery plan that depends on one person who might leave the organization undermines availability. This is why teams often use layered approaches, such as secure escrow, documented recovery procedures, and multiple authorized unlock methods, so that access is resilient without being sloppy. The Linux Plus exam is likely to probe whether you understand that keys are part of the system, not an afterthought. By the end of this topic, the main picture is that encryption at rest is about protecting stored information against offline access, and the tool choice depends on whether you want to encrypt specific objects or entire storage containers. GPG is oriented toward encrypting and signing individual files and messages, making it ideal for portability and controlled sharing, but it requires discipline and key management per object. LUKS2 is oriented toward encrypting volumes and disks, making it ideal for protecting an entire device at rest with less reliance on user discipline, but it depends heavily on secure unlock handling and recovery planning. Keys are the real center of gravity for both approaches, because losing keys can mean losing data, and exposing keys can mean losing confidentiality. Good enough is the set of choices that match the threat, keep modern cryptography, and create a workflow people can follow without constant workarounds. When you can explain these trade-offs clearly, you will be ready to answer Linux Plus questions that test practical security thinking rather than rote memorization.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.